Okay, I'm hoping today is the last day that I wear my winter weather snowy sweater. This was ridiculous, completely. Yeah, I measured 13 inches of snow, so that was crazy for April. To round out what we've got left in the semester, homework 9, I've assigned it. It is due on Monday. We'll have another day of some example problems on Friday after the quiz, where we'll talk again about the heat of reaction, heat of formation method. But I really hope that after a couple more examples, it can click and you're like, oh, okay, if I just set up the data tables, get all the heat capacity information, get all the heat of formation method, right? The sort of difficulty of translating, right, the word problem of a process is mostly in getting the process flow diagram drawn out and the material balances. Once you have all the material balances, the energy balances should almost be identical for almost any process that we do, right? It's just a matter of finding the right enthalpy values. So it doesn't matter if it's A plus B goes to C or A plus 2B goes to C plus D, right? Just write down the stoichiometric coefficients, get all the heat capacities, get all the heats of formation, right? And then just assume a reference and calculate everything. So it's a decent amount of physical work if you were to write it out. But when it comes to a homework problem or the project, it's really just add another table below your material balance table with all the enthalpy values, right? And then it's just adding up all the enthalpies times by their molar flow rates, and voila, we have our energy balance constructed. Does anyone feel quite like that yet? All right, so we're going to do some more examples on Friday, but I wanted to go over the project so we could start working on it. The project is going to be due 2 weeks from yesterday, and it's kind of like a super homework. So I'm going to go through each of the problems so we have video record of sort of what the goal of each problem is, how you should approach it, and that will hopefully speed up the process of being able to complete this project. And I'll also talk about the details of the submission. So effectively, what we're going to be doing is synthesizing methanol, so CH3OH. The most common way to do that is we react steam and methane in what is called the steam reforming reaction. And on this sheet, you have a lot of description, lots of problems, and then at the end, we have a lot of information. So this is the steam reforming reaction, methane with water, right? So it's kind of like burning it in water and it makes carbon monoxide but a lot of hydrogen. This is the process that is used to produce most of the hydrogen that we consume in the world, right? So even if you have a hydrogen car, the hydrogen you're filling up is going to be coming from methane, right? There are some efforts to try and do water splitting using solar cells or other energy sources, but it is much, much more energy intensive than this process right here. So we have an equilibrium constant here. In this particular reaction, we're forming more moles than we're consuming. So we have this leftover pressure term, right? Because we have a reference state. So this is mole fraction all divided by pressure. So we have an imbalance of the pressures. So this is what we need to do to solve for the extent of reaction based on an equilibrium constant as a function of temperature. This is a correlation for what that equilibrium constant is as a function of temperature. After we create the methanol in the water, there's a series of sort of separation steps to remove as much of that water as possible. And then we have the methanol synthesis reaction, where we further react the carbon monoxide with the hydrogen to form the methanol. Here we're consuming more moles than we're creating, so the pressure in the equilibrium term is on the bottom. And at the top, I note that all of the pressures are in atmosphere. If I go up to the top here, right? Temperatures are in Kelvin, pressures are in atmosphere, if you see at the top of the screen. For all of these reactions, we also have a simultaneous side reaction called the water-gas shift reaction. This can be used to create even more hydrogen. Again, reaction equilibrium. Same number of moles consumed is generated, so there is no pressure dependence on the equilibrium. And we have a high temperature expression and a low temperature expression for the equilibrium constant. All right? So these are just correlations. All right, so let's see if I missed anything in the process description here. So you can read this, but I'll actually just go to the process flow diagram so we can talk about it. So after this information, we have 1, 2, 3, 4 different process flow diagrams of the overall thing. So the top one here is the overall process flow diagram. So we have steam and natural gas. These are our reactants in the steam reforming reaction to produce a product called syngas, S-Y-N gas. That's that carbon monoxide hydrogen mixture. It has its own name because it's such a common process, right? So a lot of these lines here are not associated with the chemical reaction, but they are associated with the heat integration. So the natural gas follows a line here, comes down, right, gets preheated, and then goes into the burner section, and the other one will actually show more of this energy integration. Steam and natural gas react in this reactor. We recover some of the energy to make steam, to use that in a different process. The syngas then goes through a series of condensers to remove the water. Right? Water is going to be a subcritical fluid, but carbon monoxide, carbon dioxide, and hydrogen are all going to be supercritical fluids. Right? So these are going to be individual flash processes to remove that. Right? Then the syngas has a lot of the water removed. It comes down to this arrow. And then we enter the methanol synthesis section. Right? So the feed to the process is mixed with a recycle stream. Again, another flash separator. The methanol is going to be subcritical, whereas the other materials are going to be supercritical, so a flash separator is really appropriate there. We'll talk about this in a second, but then the water and methanol go into a series of distillation columns to then separate the methanol from the water. Right? So we've got our feed of the syngas. It gets pressurized. We have some waste heat recovery. It goes into the methanol synthesis reactor. That's where the carbon monoxide and hydrogen react with the water-gas shift reaction together. And then it goes out again to this separator. So we have a reactor separator loop here. So for the first steam reforming reaction, we just have a single pass, right? Single pass, condensers, removes the water. So we have one reactor, separators at the condenser, and then we have a reactor separator, and then another set of separators to make the final pure product. Okay? So all told, it's like maybe like 5 or 6 different homework problems kind of tied together into one big process. Okay? So there's this one here is sort of showing the whole thing, but we have breakdowns here of the individual processes. This is the steam reforming reactor. And I want to cover a couple of things that may be confusing. So we have natural gas, right? This is a commodity that is going to be purchased. We have the steam. The natural gas comes in at 30 degrees C, 1.6 megapascals. We have a feed of the natural gas that gets mixed with the steam, 210 C, 160 megapascals. This ratio is telling us that we're mixing 3 parts steam, Fs, to 1 part natural gas. That material is then going to be heated up from the outlet from a stream of the gas that comes out of this reactor. That's at 960 that we then heat up. So we're preheating here, right? And then feeding it into the reactor. You'll also notice that the natural gas stream here is split. Some of it goes down to synthesize the methanol. Some of it goes up to provide energy as a fuel that will be burned. Right? So these materials are entering at 30 and 210 degrees Celsius. But you'll notice by the time that they enter the reactor, they're at 450, and when they leave the reactor, they're at 855. So that energy has to come from somewhere, and that somewhere is burning methane. So what this reactor looks like is basically a series of tubes that are the reactor with a flame burning around it to heat those tubes up to get it to that process conditions. The gas that is being burned, right, so that's why we have this dashed line that connects these here. This line here is sort of saying that the whole burner is being burnt with natural gas. And you can also see that we have the air coming in. The air gets preheated to 300 degrees C from its inlet at 30. Right? So we're not wasting any energy in the process. The air comes in, it gets preheated to 300, it mixes with the methane, and that is the source of combustion energy. Question?
Is that preheating process done by like a heater, or is it from another stream that it's being preheated?
From another stream. So these are heat exchangers. So let me go over, so I just want, this part's a little confusing, so I wanted to go over it. So we have, let's go over it again from the beginning. Natural gas comes in, mixes with the steam. The steam and natural gas mixture goes through a preheater, goes into the reactor, and then leaves the process, okay? We have natural gas also going in as a fuel, F dot fuel, right? Mixing with the air at 5% excess, 30 degrees C, 70% relative humidity. That comes in, mixes, burns on the outside of the reactor. So you have flames going around tubes that are the reactor tubes. That flame gas mixture, called a flue gas, right? That's the exhaust of a combustion process's flue gas, is at 960 degrees C. We have 1, 2, 3 different processes to remove heat from that stream, and it leaves at 150 degrees C. So if I just throw exhaust gas into the atmosphere at 1,000 degrees C, I'm throwing away a tremendous amount of energy. I can use that energy into some other process that may require some of that input. So the first use is to preheat the reaction mixture because the reaction needs to take place at high temperatures and pressures. So if I don't use some of this energy, then I have to burn more natural gas to heat it up. Right? So I would have to heat up whatever the temperature is mixing 30 and 210 degrees C, right? I would have to heat that up from whatever the temperature is to 450 and then get it all the way up to 855. Right? So we're saving a lot of energy by using that. Then the next source here is this is boiler water. So this is not something you have to worry about for part 1 of the project. It's something we'll talk about in part 2. We're going to be generating steam. So we have liquid water at 30 degrees C and 4.8 megapascals. It's very easy to pressurize a liquid. So what we like to do is to create high pressure, high temperature steam. That is a chemical plant's battery. You generate steam in one location, you have high temperature, high pressure steam, you transport it to a different location, and then you can extract out that energy. So, you know, I've talked to a lot of people in my years, and on occasion you'll meet someone who will be like looking at a chemical plant, and they'll think, wow, that's such a disgusting polluter. Look at that horrible thing emitting all of those, you know, clouds of disgusting smoke. What was that? Most of it's steam, yes. You do get some flare-offs at the refineries, which is not ideal, but it's there for safety purposes.
Why don't they use the flare-off heat to do stuff?
Mostly because you don't want to you want the flare-off. So if you ever have a system that's running out to higher pressure, or if you have a reactor that has a burst disk or something like that, like, oh, there's a pressure hiccup in the system, I need to lower the pressure, you want to be able to emergency, like, send that out to the flare. And then you burn it so that it doesn't release any harmful chemicals. So the flare is an important part.
Why is the flare always running then?
So that it's ready to go, I think, whenever you need it. So I don't 100% know. The chemical process safety class will give more insight into that. But I believe it's just there so it's ready to go. And then it's sized for whatever the scope of the emergency that needs to be. But a chemical plant, because of all of this energy integration, is one of the most efficient utilizers of energy that we as a society have ever created, right? Because the scale is so big, that means there's an incentive for us to squeeze every drop of energy that we possibly can. That's why we have this complex system here where we're preheating streams that need to be heated. Any energy that we're just going to be throwing away, so any energy that we send out to this exhaust gas, that's just going to be wasted. So we might as well make some steam, and then we can use it somewhere else in the process. Does that all make sense? So they're very efficient, yes?
What is the symbol there? It kind of looks like a double, yeah,
This is a valve.
valve.
Yeah, so it allows us to control how much fuel we send versus how much of the gas we send. Yes?
And is that, on this first part, is that Fs divided by Fng, is that the mixture, or is that just the input natural gas compared to the input of the steam?
That is the design specification for the ratio of how much natural gas versus how much steam. So there's 3 parts steam to 1 part natural gas.
Okay.
In the first part of the
including the fuel part, so it's 3 parts natural gas and...
So we don't know what this one is here yet,
Okay.
right? We know what this stream is because of this design specification. So the basis that we're going to be using for this problem is 1,600 kilomoles per hour. 1,600 kilomoles per hour. It'll be clear in the questions. So this stream here is 1,600. This stream here then is going to be 4,800, so 16 times, or 1,600 times 3, right? So those 2 streams are there. And then this stream here, what its total flow rate would be and how much you need to send for the combustion, that'll be a problem for part 2 of the project, because you'll need to know how much energy or how much natural gas do I need to burn with these process specifications to get the outlet to be 855, right? Because the water gas shift reaction and the syngas reaction, they could be endothermic, they could be exothermic, right? Based on the conversion and all that kind of stuff, you'll need to know what that is. Question?
So is this steam generation process for like any specific type of plant or just a general steam?
In general, almost all plants will do this. Yep. So steam is the battery. If I have excess energy here and I need energy there, I make steam, I build a pipe, and I send them together. So your heat transfer class will talk a lot more about how do we actually design these processes here. But in general, your furnace in your house has a heat exchanger. So how your furnace works is you burn natural gas and air, and those exhaust gases shouldn't ever touch the air that's in your house. So you burn those inside of a combustion chamber with a lot of fins that are conductive. So that hot gases heat up the fins, and then you blow the air that circulates through your house over those fins. Right? So that's how those work in your house for the heat exchanger. Your car has a heat exchanger as well. Right? That's your radiator. So you have coolant going through your radiator, and your radiator has a bunch of fins and a fan that blows air across it. The design principles are the same, but in these cases, these are gas-liquid or liquid-liquid or gas-gas heat exchangers. Right? So this heat exchanger here, for the boiler water, right, you'll have exhaust gas, this one here actually, you'll have exhaust gas that will be flowing over some tubes that have water, and the heat will cause the water to boil in the tubes. So how many tubes do you need? How thin are the walls? What material do you make the tubes out of? That is the focus of your heat transfer class. Right? So we're going to zoom in at the junior year. For your reactor design class, this is where you're going to determine how many tubes do I need? How do I model this? How long does this reactor need to be? What's the residence time that my materials need to stay in this process? And that'll help you design this individual step. Right?
4 of those are next semester, right?
Basically, yes. So junior year is the, let's say, an unpleasant year, right? So sophomore, big picture. Don't worry about the details. Just don't lose mass and don't lose energy. Junior year, you will actually design each of these processes with exactly the number of tubes, exactly the wall composition, exactly the thickness. What's the geometry? Do you want the 2 materials to flow concurrently or countercurrently? Which of those gives you better heat transfer? right? So that talks about designing the actual specific units. Now, we're not even showing all of the pumps. That's your fluid mechanics class. And then the distillation columns, your separations class. And then tying it all together is, of course, thermodynamics, right? Okay. Does everyone sort of understand this chemical process? And I'm hoping this shows up nicely in the video, that this can serve as a resource to go back to as you're working on the project itself. Questions? Over here.
Are we assuming ideal mixing for like the natural gas and steam?
Yep. So for, I think, almost all of these, it'll be gas phase, so ideal gas is going to be appropriate. There's a couple instances where you have to deal with liquid streams, but for the most part, this is all going to be gas phase processes. Yes?
So on the first diagram, we had some examples of what I think are heat exchangers.
This one here?
Actually, the second one.
The one that I was on now? Or which?
Yeah, I guess the first one, yeah.
Okay.
The second picture.
So this, where they saw this convection center here,
Yeah.
that is,
Are those just heat exchangers?
yep, those are these three heat exchangers.
Okay.
1, 2, 3.
And then there's an example of a methanol condenser somewhere in there on the first one. I think it was near the bottom of that. Yeah. It's like
Oh, methanol, yeah. So this is to cool down the stream in order to lower its temperature so that you can get the methanol and the water to condense out in a flash separator. And then you have to recompress it and reheat it up. So what you're doing is, so we take some of this steam right here. See, look, see, here's some of the steam we're using, right, to heat up this stream that goes into the methanol synthesis reactor. Now, yeah, I guess we could say on this. So in this process here, they're actually injecting the reactants in different locations inside the reactor. Again, this is a junior level problem. Don't have to worry about that. That's because it's exothermic. And if you, by injecting into different locations, you get better energy distribution. Actually, I don't recall 100%, but I think it's exothermic. So you get a better sort of energy distribution so you don't get hot spots. Because catalysts, right, they're sensitive. If they get too hot, they can deactivate and then they become not as useful, right? So these all have catalysts in there to help speed up the reaction. So controlling the temperature distribution inside of a reactor is going to be important. Okay, so then that comes down. Some of that energy, right, is taken away from the process to preheat the stream to get it to a high enough temperature that the catalyst becomes active. The reaction will happen readily, but it doesn't get so hot that it deactivates the catalyst. Okay? Then we will send it out down here through and preheat the stream again. Right? So we're using the energy, we're collecting some steam here as well, right? Then we're going through some fans and some cooling water to drop the temperature further, such that the water and methanol will be able to condense inside of the flash separator. Then it goes back, it gets recompressed, repressurized. This heats it up a little bit, and then we get more energy back through each of these individual streams. Then we have our recycle with the purge. So this unit right there, that's the splitter, that's the mixer. All of this stuff here, you can just ignore it for the most part on part one. Reactor, separator. Liquid stream, vapor stream. Those are the two products. And then we have a series of distillation columns because the methanol water system is not really an ideal mixture, but you're not going to have to model the non-ideality here. We're just going to tell you what the composition of these streams are, and you just have to balance the material balance. Yes?
So for the sake of this project, we can treat those three streams going into the,
At this stage, yes. Yep.
treat it as one stream?
Yep.
Okay.
Don't have to worry too much about that. Because we're doing the overall big picture process. We are not modeling what is the temperature distribution inside of the reactor. So if I was really building this reactor, and this reactor would probably cost on the order of tens of millions of dollars to construct, right? So $50 million doesn't seem out of the ordinary. It could be even more expensive, on the order of $100 million to build this reactor. Yes. So this is the Methanol Synthesis Reactor College of Engineering, right? So this reactor is going to be very, very expensive. And that's also including all of the, the equipment and parts associated with it. So as chemical engineers, maybe it's worth it to run a couple of computer simulations to see where we should actually put the injection ports. Let's confirm that we're not going to deactivate our catalyst and we can actually make the methanol product at the rates that we think we can to sell it.
Would deactivating the catalyst trash the whole reactor?
It would basically, if the temperature runs away, that this becomes like an explosion risk, then yes, of course it would trash the whole reactor. But the catalysts inside are going to cost millions of dollars a year probably.
That's not that bad.
Not that bad, right? So if you deactivate the catalyst, there's a couple of things that go wrong. One, you got to buy a new catalyst. Two, you got to figure out why your temperature got out of control. Three, you have to shut down the entire chemical process until that problem is fixed. So the biggest cost is probably going to be the delayed profit that you're actually not making product, right? And the other thing is, too, these places, they have contracts. They say, I'm going to buy this much methane for this period of time at this price. And if you're not buying the methane, someone else is like, well, what am I going to do with all this methane? Right? And there was a time period right at the beginning of the pandemic where the price of oil became negative. Does anyone remember that in the news?
Oh yeah, that was so cool.
Right? That's because everyone said, I don't want this oil. I don't know what to do with this oil. If I refine it, none of my gas stations can take this oil. I've got nowhere to store it. So the best option I have is to pay someone to take this oil off of my hands, right? So when we have a big hiccup in these chemical processes, the biggest refineries in Southeast Texas and across the world are on the order of about 500 to 750,000 barrels of oil per day, right? So imagine a barrel, and now 500,000 of those are going through one big refinery per day. And this also explains why chemical engineers are very conservative. Do you want to be the individual that does some clever change in the process?
Do you say conservative as in like...
Not politically conservative. Conservative,
You're dead wrong.
conservative with respect to making changes to processes. You'll often hear, well, it works. And that's the reason why we do what we do, right? Because do you want to be the individual that has to figure out what to do with 500,000 barrels of oil on Wednesday, 500,000 barrels of oil on Thursday, 500,000 barrels of oil on Friday, and so on and so forth? That is a massive, massive hiccup, right? You got to turn oil tankers around and have them reroute and go sell their oil to someone else. It's a big, big issue. So that's why they like to spend a lot of time designing it, and they like to do a couple of tweaks when they start it up, but then once it's humming, and if they're making money, they don't care. They don't want to change it because you do not want to be responsible for not producing the product, for not buying the reactants, right? So that's why chemical engineering, I think, is a little bit distinct from all the other engineerings, right? This is the conventional chemical engineering. Not every chemical engineer does this, right? But it's still a very large component of our economy, and it's one of the main reasons why chemical engineers get paid a lot. Now, a lot of the modern jobs in chemical engineering apply these principles to smaller things, right? Biological processes, biological devices, semiconductor manufacturing. Similar principles, smaller scale, right? Same concepts, heat, mass transfer, thermodynamics, yes?
So what I'm hearing you saying is that we're more important than other engineers.
Not more important. Like, we all drove a car here, probably, or took some sort of train or bus. I'm assuming not many people biked to school today, okay? Right, so there's a lot of things that go into it, but one of the challenges of chemical engineering, and I really hope you guys bear it out, is that in order to do this chemical process to completion, you can't do it. A team of people can do this. To even understand the problems that you may encounter requires 3 to 4 years worth of education, right? Where do I inject my chemicals into this reactor so that the exothermic reaction doesn't create local hotspots and deactivate the catalyst? Okay, what's a catalyst? Okay, how do you know what the rate of reaction is? How do you know the fluid mechanics and the heat transfer to determine how quickly does the heat dissipate? So in order to build one process in the plant, you need to have 3 or 4 different advanced engineering classes to make progress on that. Now, there was a question about, hey, what was that weird symbol back there? This symbol right here. This little symbol is a valve. So, this pertains to your senior year, controls class. You will be measuring the outlet temperature of this chemical reactor. And you realize, oh, my reactor temperature is dropping. What do I do? You say, well, I can increase the amount of fuel, and I can increase the amount of air, and I can just burn more methane to get that temperature up, right? Maybe the catalyst is getting towards its end of its life, and you need to increase the temperature a bit. How do I get more natural gas into the process?
Open the valve.
How much? How much do I open the valve?
Figure it out.
Well, but if the temperature continues to drop, do I open it really quickly? Well, then the temperature gets really high. So the only thing that I can do to actually influence this process is turn pumps on, turn pumps off, turn fans on, turn fans off, open valves, and close valves. So I need to know, if I open this valve a little bit, how much extra flow rate is going to come out of that? How quickly do I open that valve so I don't create an unstable system where the reactor gets too hot and then can get damaged or can actually explode? That is process controls. How much do you open the valve, right? So the entire chemical process and understanding how to do all these different steps is necessary to have basically your entire bachelor's degree in order to actually practically build this. And that is why we don't have cute little egg launching cars like mechanical engineers do, right? Because at the freshman year or sophomore year, we cannot construct the actual thing that we're aiming to construct, right? So chemical engineering has a little bit of a downside. It's a bit virtual. It's a bit abstract, right? It's a lot of pen and paper, a lot of thinking, a lot of mental visualization, but it does pay off. And this is why chemical engineering was listed as the best paid undergraduate degree this year. And it has been for a very long time. Right? Sometimes petroleum engineers will edge us out, but that ebbs and flows a little bit. Chemical engineers are always pretty consistent. Okay, questions about the process. Then I'm going to go over the problems. Yeah, question.
Process as in like this process or the product?
The process that you will be working on.
Are we allowed to assume everything is like ideal, like there's no heat?
I believe most everything is ideal mixture, ideal gas, except when it involves boiler waters and flash separators and distillation columns. But all the reactions, almost all these flow streams are going to be ideal gas streams. They're high temperature. Even if the pressure's high, they're still ideal gas is totally appropriate. Back to your question.
Did you go down to the second one? I don't know if I remember.
This one here?
No.
This one here?
Yes, yeah, that one.
Top part or bottom part?
Bottom one.
Okay, gotcha.
What is the light and?
Those are just different.
Yeah, so these are 2 different distillation columns. So they might be distilling out other products that are not listed in our process flow diagram. Like you could be making some formaldehyde or acetic acid. Right? You could be making a couple of other different chemicals. Actually, acetic acid will be lower vapor pressure, but you could be making other compounds that are not being considered here. And this could also be a way to break the azeotrope. I'm not sure if methanol and water form an azeotrope. I'd have to check. But this could be just for some other products. But for the purposes, we're just going to model this as one big separator. Yeah. So you don't have to worry about these light ends, but good question. Okay, there's a question back here.
Could you give some of the most common uses of methanol or some of the industries that need it?
I think methanol, there's better descriptions, and I should have read up a little bit more on it. Very common solvent for a lot of different processes. I think it's also used for polymerization as well, maybe as a solvent for chemical processes. But I think it's a chemical precursor for a lot of things, right? So if you want to attach like if you want to make like an ether or something like that with a methyl group, then you'd want to snap a methanol onto things. So I can get back to you, but the description, I'll have a better answer on Friday because I should know more uses of methanol. Okay, so let's go over the questions. So before I go over the questions, no, actually let me go over the questions, then I'll go over the reporting. Okay, so question 1.
Ethan has a question.
Oh, yeah, Ethan, yes.
With the distillation columns, are those like using Raoult's law, like the flash separators are?
No. So for the distillation columns, it's going to be like old school start of the class. This is the inlet, this is the outlet compositions, balance the process, right? So I think the goal of these distillation columns, and it's in the problems, I think it's like you want to recover 95% of your methanol, and the product stream has to be like 99 point something percent pure. And so then you just have to figure out what the other streams need to be.
So it's all just balancing. There's no like.
For that one, yes, all just balance. All of these are just balances, yeah. They're just mass balances, and then part 2 will be energy balances. There'll be reacting systems, there'll be phase changes, there'll be non-phase changes. So, no, it's not too bad. The hard part is in the organization, so I'm going to go over that and go over the problems really quickly. So number 1, again, hopefully this is showing up well, but if not, follow along at home, people on the video. Number 1, okay, your goal is you need to make 4.3 times 10 to the 5 metric tons of methanol a year. That's a lot, right? You're going to operate 350 days of the year. When you're operating, you're going to be 24 hours a day, so that gives you 15 days of downtime throughout the entire year to make changes, fix things, replace pumps, and so on and so forth, right? So that's going to be the downtime. So then you need to calculate how much methanol you're going to need, how much methane, and how much steam. Okay? So this is just an overall input and output. And this is basically going to give us our basis for what we're going to do our calculations on. Right? This is how much we need per hour in terms of our material. Okay? So this is effectively just a fancy unit conversion. Right? That's what that problem is. Okay, part 2, this is talking about the methane and burning. So what are the flow rates per kilomole of methane fed to the system, right? What's your molecular weight of the air? Because we have to factor in the humidity. Why does the molecular weight of air differ from that humid air of dry air? And then what is the flow rate that we need of air per kilomole of methane burned following these process specifications, right? So this is just a relatively straightforward combustion balance process, but you have to add in the humidity and see how that affects your flow rates a little bit, okay? Seem okay? Not too bad so far, right? Sort of like it's like a super homework. Some of the problems are easier, some of them are a lot harder. Okay, question 3. So we're assuming a basis of 1 kilomole per hour fed to the burners, okay? This is asking you to balance the process. So what is the composition of the flue gas? And then based on the process specifications, and this would be the 150 degrees C outlet, right? What is the volumetric flow rate going out? And there's a part C, I think. What is the specific gravity of that flue gas stream? And why does it need to be greater than or less than that of the surrounding air, right? So thinking about those problems, okay? So again, and one thing I want to note, these little stars here, so these stars are the ones you want to focus on.
Wait, this is due on Monday?
No. Homework 9 is due on Monday. This is due 2 weeks from yesterday, so you have about 2 weeks to work on this. Okay. These star problems are the special stars of the project. They are the ones where you are actually balancing the process and you're linking everything together. So the problems that don't have the stars, those are kind of independent problems, right? Helping you better understand the inlets, the outlets, the overall calculations. But the star problems, these are the ones that you will put into your overall process flow chart and balance the entire process, okay? So this is the steam reforming reaction going to the condensers going to the methanol synthesis reactor separator, and then the separators to make the methanol product. Those are the star problems, okay? And I'll talk about this in reporting a little bit. So the methane fed to the steam reforming reaction at 1,600 kilomoles per hour. This is our basis for the whole project. 1,600 kilomoles per hour is our basis. This does not include the steam that goes into combustion, but we're not worrying about where the energy comes from right now. That's going to be a problem for part 2 of the project. Okay? So then what we're asking is, what is the composition of the outlet stream based on the chemical equilibrium and the conditions that are listed in the process flow diagram, right? So that is going to be the steam reforming reaction and the methanol synthesis reaction occurring simultaneously. Oops. Let's go to this diagram. Here's a little easier, right? I believe the outlet equilibrium composition of 855. So based on the ratio 3:1 of steam to natural gas, those two reactions occurring simultaneously, you need to get the equilibrium constants. You need to solve the system of equations to figure out what are the extensive reactions for the steam reforming reaction and the water gas shift reaction, and then tell me what is the composition of this outlet stream, right? How much hydrogen did you make? How much carbon monoxide did you make? And how much of the unreacted methane and steam remain in the system? Okay, make sense? Yes?
The equilibrium constant isn't directly equal to extent of reaction, right?
No. So we have a couple of homework problems. This was around homework 3-ish, homework 4-ish, where we did the extent of reaction. And remember, we set up these mole fractions as a function of the extent of reaction so that we would have, so for example, the carbon monoxide participates in both the water gas shift reaction and the steam reforming reaction, right? So you'd have to have extent 1 and extent 2 in both of these expressions. So you'd have to solve that system of nonlinear equations together. Going back to number 4, our first star problem. So this 3:1 ratio is the actual process conditions, and I have a little star, and then I'm telling you to report these flow rates into the material balance summary table in the template. So I'm going to quickly switch over to that template. Oh. Okay, there we go, we're back. So I have uploaded this template because there's a lot of questions. This helps my grading, and it also helps you to be organized to make sure that you're answering all the parts of all the questions. So what I have here, right, I have a spot for you to put in the answers for all of the individual calculations, right? So problem 1, problem 2, right? Why is this value of specific gravity, right? So that's like 2B's problem. Okay, problem 3, problem 4. Here I'm asking for you to plot the composition of the outlet at different steam to methane ratios so you can sort of see what decisions chemical engineers make. Like, why do they choose 3:1, right? Why didn't they choose 2:1 or 1:1 or 5:1, right? So this allows you to kind of play around with that a bit. And then so there's spots for all of them. So this table right here, this is the summary table. So when I say put the flow rates in the summary table, that's what I mean. So the steam reforming reaction effluent for problem 4A goes right there, right here. And then you'll have after the chiller, after the methanol synthesis reaction, the purge composition, and then there's your top and bottom streams of the actual final products. Okay? So if you're doing Excel, I want this sheet to be the first worksheet, and then you copy a link to all of your calculations so that I have a summary of all of your work in one spot. If you are using Python or MATLAB, you have two options. You can either copy them over here and just paste the numerical values, or you can work your code so that it formats it so it spits out and summarizes the answers in a really clear, coherent fashion, right? So I don't want to have to look through 700 lines of code to be like, there's the answer to part 1, right? So your code needs to spit out the numbers that I can actually read them in some table so that they're labeled with the right units and everything, okay? So you can either copy and paste the values into here or format your outputs with like fprintf to make it clear, like, here's question 2, here's the answer. Here's question 3, here's the answer, right? So I need to actually get the data out of your code if you're going to use Python or MATLAB. Is that clear? Okay, good. So that's what I mean by adding things into that summary. Oh, come on. Okay. So part 4B is saying resolve A, right, but do it for different ratios, and then plot the flow rates of CO and hydrogen, so just so you could see how they change if you change the inlet conditions. Because when you're designing a chemical process, you don't know what the exact right answers are. And so you have to actually balance and optimize the whole process to figure out what is going to be the most profitable combination. Because if you add more steam, you might be producing more carbon monoxide and hydrogen, but then you have to spend more energy removing that excess water or in the distillation steps, and so you might be causing yourself more problems down the road just to squeeze out a little bit more hydrogen out of the process. So it's a balance of everything. But you notice B doesn't have a star, so that's as a little side quest, a little side question, right? Okay, so number 5 is for those condenser streams. So we're going to remove the unreacted water because we don't want that water in the methanol synthesis reactor. We're just going to have to remove it anyway in the distillation columns, right? So this is just asking for what's the dew point of the stream, how much water would you remove, and then report the flow rates of the stream exiting the condensers of how much water you've removed. Okay? Question 6, again, no star. This is another side quest. This one is asking you to do exactly the same thing for the steam reforming reaction as the methanol synthesis reaction. Solve simultaneously for the methanol synthesis reaction and the water gas shift reaction for the process conditions. Okay? Now, the reason why we're not going to be doing this for part 7, which is the actual star problem, is because it's very, very complicated. Because you would have to solve a nonlinear equation as you're doing sort of an iterative loop. Okay, number 7. This is the big baddie of the project, right? This one is where you balance the reactor separator process. We're going to talk about a strategy using something called a tare stream. So what we will do, come on, projector, give me some. Okay, so let's go to the methanol synthesis reactor, and it is here. Okay. So this is a simplified process flow diagram for the reactor separator. So we're going to have our syngas that has the water removed. That's part question 5, right? And then it's going to mix with the recycle stream. The way that they've reported this is that the flow rate of the methanol synthesis reactor, so this stream right here, is 7.8 times this stream here. That amounts to a recycle ratio of 6.8. So if I have 6.8 being recycled, I have 1 coming in. That means the total combined is 1 plus 6.8 is 7.8. So I tried to make that clear in the project description. Now, the challenge here is that you don't actually know what the composition of this stream is. The reason why they have the recycle ratio fixed like this is because they control valves, right? These are gas phase streams, so we can control the relative volumetric flow rates. But we don't necessarily know what the composition of this stream is, but we're keeping the recycle ratio as the design specification. So this introduces sort of a tricky way of how we can solve this. In these processes that have loops and that are very chemically, are very complex, they're difficult to solve numerically. So strictly speaking, you could probably set up a system of equations and get the right answer, but there's an easier strategy, and that's something called a tare stream that I will talk more about as we get into the project a little bit more. But basically what we do is we've got this flash drum, that's our separator. So we have coming in, we have feed, recycle, mixer, reactor, and it's a kind of circuitous path that it comes down around up here. Separator, splitter, purge, recycle. Right? So there's a reactor separator, just drawn a little bit differently. What we will do in solving this problem is we will cut this line here, the recycle line. And what we will do is we'll sever this line, and then we'll just make a guess of what we think the recycle composition is. Right? Then we'll mix. Well, that's just adding 2 streams together. That's really easy, right? Then we'll go into the reactor. We'll have a set conversion, so then we can calculate the outlet compositions of the reactor. Well, that's really nice. Then we'll go to the separator, and we'll perform a flash calculation where we know the feed conditions, so we can calculate the liquids and the vapor top stream. That's really nice. We have a splitter, so we know how much we're purging, so we can directly solve for that. And then what we will do is we will copy the top that's being recycled here to this one down here. And that's using a tare stream. And then you iterate and copy and paste, 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 and then eventually the solution will iteratively converge to the equilibrium steady state solution. So we'll talk more about that, but that's the strategy if you wanted to try it out before we get to that point. Okay, so let me just wrap this up really quickly because we're going long on time. That's 7. So 7's the doozy. 8 is just balancing the distillation columns, right? So that's just a non-reacting material balance. And then number 9, the last part of number 8 is asking you how good of a job did you do? Did you make as much methanol as you needed to make? Okay. And then the last part is perform a total mole balance. Did you lose any moles in your process? Okay. Question.
So what is part 2 going to be like?
Just doing the energy balances in all the processes. But the thing is, right, the energy balances are super, super, super algorithmic. If you have all of the heats of formation and all of the heat capacities for all of the materials, it's just summation of molar flow rates and enthalpies. Add them all up, that's your Q, right? So hold on, one sec for questions. So reporting, I'm losing it again. So reporting, one PDF with all of your handwritten calculations. One computer code with all of your calculations. The only exception to that is if you're solving it in Python and you want to copy it over into the template, then you can upload 2 computer files, right? One handwritten, one computer code, well commented, well documented, easy to follow and organized. If it's not organized, I will be mad when I grade it. But you will also struggle extremely hard on this project. The more organized you are, the easier it will be for you to troubleshoot. You will spend 90% of your time troubleshooting, not actually solving the problems. Okay? So the more organized you are, the quicker you will be on this project, and the happier everyone will be. Grading, 50% is the accuracy of the calculations, 30% is the organization of your computer tools, 20% is the organization of your handwritten calculations. Okay, that's all. Sorry I ran long, and I'll handle some questions after I end the video. Okay, see you everyone.